In this lecture, we're going to use a rather popular sport to illustrate the kinematics of throwing a football in terms of general motion. And what we're going to focus on is something called the forward pass. And so what we see here in these two photographs, here we see two quarterbacks that during the course of play are throwing the ball, or rather passing the ball, to a receiver downfield. And so our question really relates to the trajectory of the ball being able to travel the necessary distance accurately, but in order to do that, the kinematic pattern of the passer here is going to be critical, and that'll be the focus of this lecture. For those of you that have an interest in the history of the football forward pass, although this is not required viewing, I encourage you to click and connect to this YouTube video. It's a 1-hour documentary, a very interesting one, I think, on the history of the forward pass. But when we take a look at the forward pass in football, it is kinematically defined as general motion. So in this montage of a passer, we can see that this passer is preparing to throw the ball, and the whole body is actually moving in a forward direction. That would be linear motion. The arm is moving in a forward direction in a linear fashion, but we also have rotations about the trunk and rotations about the arm itself, and the combined action of all of that movement will contribute to the trajectory, the distance, and the accuracy of the throw. And so what we're going to focus on here in our example is we're going to focus on the kinematics of the arm. Particularly, we're going to focus on the forearm, hand, and ball as a means of predicting what that distance of the ball will be. And so to understand the biomechanics of the movement of this task, we're going to tap into a study published in 1996 that examined the phases of passing a football. And so we see in this study there are the process of throwing a football is broken up into a number of different phases, and it starts with what's called the wind-up phase, followed by a stride phase where the passer steps forward. The arm is moved into a rear position, what's referred to as arm cocking. The arm will then accelerate from this position to increase the angular velocity of the shoulder and elbow. And at some point when that velocity peaks, the arm will start to decelerate. And then the follow-through is the completion of the pass. But as we move to the wind-up phase, this is a very critical phase because this is the point where the passer takes advantage of Newton's third law. And the GRF stands for the ground reaction force, which is generated when the passer plants the rear foot against the ground forcefully, causing the ground to react with a force that is equal and opposite in magnitude and direction. And it's this ground reaction force that will be the impetus propelling the passer into the stride phase, so pushing that athlete in a forward direction. That will also cause the athlete to engage in pelvic rotation, and that force, as it's transmitted from the ground into the foot, ankle, lower leg, across the knee, into the thigh, and across the pelvic and hip region, will generate that pelvic rotation. And so something we discussed earlier, that forces compels motion. And so this force being transmitted up along the chain will compel the pelvic rotation, will compel the trunk rotation, and then the arm will not only rotate, but will also move in a linear fashion in the direction of the intended passing of the ball. And so rotations will occur at the shoulder and elbow to compound on top of the existing linear motion of the arm, and that will all contribute to the intended trajectory of the ball. And so in this study sampled 26 established quarterbacks. 13 played at the university level, 13 were high school quarterbacks, and each participant in the study, each of the 26, came into the lab, as you can see here. Motion analysis video capture was used. These markers identifying the joints were used to track the movement patterns so that the kinematics could be calculated from each of the 10 passes that the athletes completed, and they were to throw the ball at a target that was approximately 20 yards away, or 18.4 meters away. And so, and the pattern or the path of the ball was also tracked in the study. So in terms of what was observed, the average ball velocity at release was slightly over 20 meters per second. The maximum velocity of elbow extension, as we can see from the cocked phase into the arm acceleration and deceleration phase, on average was over 1700 degrees per second, so it's a fairly fast movement. The maximum pelvic rotation velocity was recorded to be 500 degrees per second, and we also see a very fast trunk rotation velocity of 950 degrees per second. So notable here, we see that as we move from the pelvis to the superior trunk to the superior elbow extension, we see a progressive increase in the angular velocities along that chain from the foot all the way up to the arm that is holding the ball. So if we examine the different phases here in passing the ball, if we take the ball release to be 100% of the entire process of passing the ball, the maximum elbow velocity was achieved just prior to ball release, 95% of the total movement. The maximum trunk rotation velocity was achieved at 62% into the movement, and the maximum pelvis rotation velocity was achieved at 56%. So we can see that in order to pass the ball, the vast majority of the movement occurs during the wind-up and into the stride phase, indicating that this process is critically important to a successful throw. Now, what we're going to do here is we're going to focus on taking a quantitative approach to tracking movement of the ball, and we're just going to focus on the forearm and hand, remembering that we have to couple linear motion along with angular motion to finally arrive at general motion, which is the characteristic pattern in passing the football. And so our examination here is going to be highly simplified, because we're going to take a three-dimensional movement and we're going to simplify it in two dimensions. As was indicated in an earlier video, what's very important here is that when we start the process of taking this quantitative approach, we simplify as much as possible so that we establish the foundation for the analysis that will allow us to build back into the analysis complexities that are a little bit more realistic. And so if we track the linear path, assuming two dimensions here, so we track the linear path of the elbow from the cocked phase into the point where the ball is released, we can describe those and quantify those as vectors. And so we have a velocity of the elbow, a linear velocity in the x direction. We can quantify a linear velocity in the y direction, as if we watch the elbow, it moves from this position to this position. Now, because the forearm and hand and ball act as a single unit, we can translate the elbow velocities into the ball velocity at the distal end of that extremity. So the horizontal velocity of the ball will be the same value as the horizontal velocity of the elbow, as will the vertical linear velocity of the ball will be the same value as the vertical velocity of the elbow, just at the instant prior to the release of the ball. So the manner in which we would go through and examine this situation quantitatively is that we want to compute the kinematics. So we're only focused on the motion and not the forces that are involved in passing the ball. So in identifying our objective here, we want to eventually determine the distance thrown, how far the ball travels, which is going to be a function of three main factors. Those three factors are the release velocity, so how fast the ball is traveling at the instant it breaks contact with the hand, the angle of the release of the ball with respect to the horizon, and the height of release from the ground. All three of these factors will determine that distance thrown by the ball. So the very first step here is that we need to model the forearm. How are we going to model the forearm? We're going to model the forearm, hand, and ball essentially as a single rigid segment, and we're going to take a two-dimensional approach at this point. So here's our constructed model for the forearm, hand, and ball. And so, of course, we always have to have our frame of reference. We'll tuck this down here at the bottom corner of the screen, where the X, Y, and any rotations counterclockwise are all positive directions. We know the forearm length. This is going to be a given. It's 0.37 meters, and that represents the radius of the forearm. Remember, what we will have here is a rotation about the elbow eventually, so we do need to know that length of the forearm to compute the kinematics. The y direction velocity of the elbow is sampled to be 1.2 meters per second, so this is always going to be a given. And it's a vector. Velocity is a vector, and it's directed upwards. The horizontal, or the x direction velocity of the elbow was sampled to be 3 meters per second in these indicated directions. So these two vectors represent the two components of the elbow velocity. And there is also a rotational velocity. If we just focus on the pure angular aspect here, we'll take a value of 31 radians per second for the angular velocity of the elbow. Recall that we have to have our angular measures in radian units in order to carry out a full kinematic analysis of a rotating segment. Focusing purely on the angular, so for a moment here, we're going to ignore the linear velocities of the elbow and just assume that this segment is rotating purely about this axis. We know that it's going to form a circular arc related to that angular motion, and as a result, that ball, the distal end of this segment, will have a tangential velocity that is going to be directed purely horizontal. And that's the linear component due to the angular motion. So we're going to assume here that the ball will be released at the instant that the forearm is perfectly vertical. So here we're just going to separate the linear and angular components to the movement. So here we see the initial position of the forearm segment. Here we see the final position of the forearm and hand segment. And recall that the horizontal velocity was 3 meters per second, the vertical velocity is 1.2 meters per second, and because the segment does not change shape, these velocity values translate to the identical values at the distal end where the football is located. So as the elbow moves in this linear fashion, so does the football. Due to the pure rotation aspect of it, we know that the elbow is rotating at a rate of 31 radians per second, knowing the length of the segment to be 37 centimeters or 0.37 meters. The tangential velocity, let me go back one, the tangential velocity will be a function of these two factors right here. So we have the pure linear component, we have the pure rotational component, and what's critical here is the total ball velocity, the resultant ball velocity, which is going to be the vector sum of the x component of velocity and the y component of velocity. So if this vector represents the resultant of the ball velocities, which is the important value here, we know that this is going to be the vector sum of the vertical component and the horizontal component. Now, because the ball is going to be released at the point in which the forearm is perfectly vertical, the only component to the tangential velocity due to rotation will be directed purely horizontal. So there will be a zero vertical component here. Therefore, the only vertical component to the ball is the one that was experienced from the vertical velocity of the elbow that we see here. However, we start to see a few additional x velocity vectors. The first one is the velocity of the elbow in the x direction, and this translates to the ball. And we also have the tangential horizontal velocity. If the ball was released earlier, then there would be a vertical component, but we're not going to worry about that at this point. So we have the ball, the linear velocity of the ball in the x direction due to the movement of the linear movement of the elbow. We have the we have the horizontal ball velocity due to the tangential component of the rotation, and the total ball velocity in the x direction is just simply the sum of these two values here. We don't have to worry about the direction because they're all directed horizontally. So although I subscripted the total term here for the total ball velocity, I put it in a normal font just to highlight the fact that this is a total velocity, which is the vector sum of the x ball velocity and due to the movement of the elbow, and the tangential due to the pure rotation component. So this would actually be a good time to pause the video and to go through this calculation and then restart the video in order to check your answer. Okay, so assuming that you pause the video and you're restarting it right now, we're going to fill in our equation with the information that we have, what we know. And what we know is that the ball already has a horizontal velocity due to the linear movement of the elbow at 3 meters per second, and we know that the tangential velocity of the ball is a function of the length of the rotating segment times its angular velocity. And so as we substitute the numbers and we perform the math, we end up with the value of 11.47 meters per second for the tangential velocity of the ball, ignoring the linear aspect, but then we add that to the linear aspect for the total velocity, and we end up with a total movement velocity of the ball in the x direction of 14.47 meters per second. Now recall that we already have the y component here for the velocity vector at 1.2. Recall that the 1.2 was the vertical velocity of the elbow, which translates to the vertical velocity of the ball. There is zero vertical component due to the pure rotation, so we just have this one right here. So knowing that, The resultant, this is the key variable that we're looking for here, is that resultant velocity of the ball. That's going to be the vector sum of the total velocity vector in the x direction and the total velocity vector in the y direction, which happens to be just the one that we observed earlier with the elbow. So using Pythagoras' theorem, pause the video once again, run through these calculations, and then restart the video to see if your values come up with the same ones here. Okay, so assuming you're restarting the video here, we substitute the values we just computed, we run through the math, and we find that the resultant length of this vector, the resultant velocity of the ball, is a total of 14.52 meters per second. And that is one of the factors that's going to determine how far the ball travels. So in terms of the release angle, which is the next factor that's important in how far the ball will travel, that's going to be equal to the arctangent of the vertical component divided by the horizontal component. Once again, presumably you've paused the video and you're restarting the video. We substitute the numbers and we find that the ball release has an angle of 4.7 degrees from the horizon. And that's going to be an important consideration here because the ball will follow a parabolic path. Now, to determine how far the ball will eventually travel, we have this equation here that will determine the distance of the flight. And so, although we won't go through this in this video, we will cover and go through this equation in the video on projectile motion. The key items to make note of here is the theta, which is the release angle. The v is the resultant release velocity of the ball, and we see that appears over here in this term and in this term as well. G is the acceleration due to gravity, which is 9.81 meters per second squared. We see that G is here as well. And H, which was not given in the problem but will be given, is the height of the release from the ground, which is going to be a function of the height of the passer and their arm length. But this ends this video on quantitatively examining general motion of a functional task.